And this time, as we continue our study of the periodic table of the elements, we're going to figure out how we come up with some of these chemical formulas that we've looked at. H2O, NaCl, sodium chloride, magnesium fluoride, MgF2, and some other formulas, as you'll see throughout this set of notes and our practice exercises coming up. So how do we write the correct chemical formulas? That's what today's lesson is all about. Are we ready to begin? What is a chemical formula? Well, we've seen some already. Here is your definition now of chemical formula. The formula that shows the exact number of all the atoms that make up the molecule. So the exact number of all atoms in that chemical formula. You've seen this formula a few times already. Glucose, a type of sugar. Probably the most common type of sugar, what we think of when we say, hey, pass me the sugar. C6H12O6. The 6 that's after the C means exactly 6 carbon atoms in this molecule, and then 12 hydrogen atoms, and then 6 oxygen atoms. And notice the subscript, the number, always goes to the bottom right of the element atom that the number represents. So again, for glucose, 6 carbons, 12 hydrogens, and 6 oxygens. C6H12O6 for glucose. Ready? In a chemical formula, here you see another example, nitroglycerin. The subscripts, again, they are the bottom right of the letters. So in nitroglycerin, a very explosive liquid, 3 carbons, 5 hydrogens, 3 nitrogens, and 9 oxygens. Now the arrangement has to be just right as well, not just the correct number, but of course the molecule is going to be arranged the same every time. We call those numbers subscripts. They come below the symbol and to the right. So look at the C3. That means 3 atoms of carbon, then 5 atoms of hydrogen, and so on. 3 nitrogens and 9 oxygens. The subscript is always to the bottom right of the atom's chemical symbol, and in the molecule we can now easily tell where the next element begins. So once again, the subscripts are the numbers below, actually bottom right of the symbol, to tell exactly how many of that atom makes up the molecule. Ready? Oxidation numbers. You got a handout recently that showed you what's called oxidation numbers, some positives and some negatives. Well, remember, electronegativity deals with the likelihood that an atom will gain electrons. Well, remember, metals give away electrons, and they also have oxidation numbers. Oxidation numbers tell how many electrons an element is likely to gain or lose or share in a reaction. Remember, your nonmetals gain electrons and they end up with a negative charge. The metals lose electrons, and because they now have more protons than electrons, the metals get a positive oxidation number. So the losers end up positive, the gainers of electrons end up negative. And remember, in covalent bonding, the atoms share in the reaction. They share the valence electrons. Now, some elements, particularly the transition metals and many of the nonmetals, they will have more than one oxidation number, which means depending on the other atoms involved, the elements won't always use the exact same number of electrons every single time. Most of the time, yes. In fact, you look at those with more than one number listed, you'll see on the handouts, the first one listed is the most likely oxidation number for that particular atom. Now, these are also called valence numbers, and that's because they're referring to the valence electrons. So oxidation numbers are how many valence electrons, but sometimes the core electrons are used, mostly valence. So how many valence electrons or electrons an atom is likely to gain, lose, or share in a reaction. Ready? For example, the alkali metals, they will lose 1 electron. Well, we've seen examples like this before. Sodium has 1 valence electron, and chlorine, which will become chloride, has 7 valence electrons. The sodium is very likely to give away that 1 electron. So sodium will end up with a positive 1 charge. Therefore, the oxidation number of sodium is +1. Chlorine will end up gaining that extra electron to give itself, remember that magic number of 8 total valence electrons, and by doing so has just gained a negative charge. So the oxidation number of chlorine is -1 because chlorine is very likely to add on 1 electron. So the alkalis are going to lose 1 electron, so the alkalis have oxidation numbers of +1. You'll see that on your handouts. Alkaline earth metals have 2 valence electrons to give away. So the alkaline earth metals have oxidation numbers of +2. Again, some have more than one number. The first one listed is the most likely oxidation number for that particular atom. Halogens, I just showed you chlorine. Halogens are going to add on 1 valence electron. So halogens have an oxidation number of -1. Now what about the noble gases? Their oxidation number is 0. Now remember the definition of oxidation number. How likely the atom is to gain or lose electrons. Why will noble gases have an oxidation number of 0? Remember, they don't react with anybody else. Therefore, they're not going to add on or lose any of their valence electrons. So the noble gases have oxidation numbers of 0. Now again, I've said this a few times already, some elements have more than one oxidation number. The oxidation numbers vary. On your handout, the one listed first is the most likely one to happen for that particular atom. Ready? Oh, the total molecule. Sometimes I forget there's a line right there on the bottom that sneaks in. When we add up the oxidation numbers, since some are positive and some are negative, we have to get a 0. If we do, we've done this job correctly. If we don't get a 0, now we know we've made a mistake. And as we do practice exercises, that'll come more and more into play. Now we're ready. Here are some example oxidation numbers. Iron 3 oxide, which is the chemical name for something we commonly know as rust. Well, iron is Fe. Now, oxide, that comes from oxygen, that is O. Okay, now you notice that iron has 2 possible oxidation numbers, a +2 and a +3. But oxygen has only 1, so let's start with the oxygen because that's an easier one. Oxygen's oxidation number is -2. Now, if we're talking about a different iron oxide, then I could just say iron is going to be +2, and I get +2 and -2 would equal 0. But that's not the case. See that Roman number 3 right there? Remember, iron could be either +2 or +3. Well, you know what? This tells us exactly which one of those 2 numbers to use. We're told right here, use the +3. And there we go. Does this total 0? +3 and -2 does not total 0. We have to make this total 0. Now, I can't just say, hey, 2 times something is 3. That ain't going to work. But I can do something called the least common multiple. What's the least common multiple of 2 and 3? Well, that is 6. So what I need to do is get both of these to equal 6. Well, how many +3s make 6? 2 of them. How many -2s make -6? 3 of them do. This, when added together, equals 0. It'll be a little neater when I put the typed words up there. Fe2O3 is the formula because oxygen has an oxidation number of -2, which I would put right here, and that would give me a -6. In order to cancel -6 and get 0, this has to be +6. Well, what twice is +6? That's +3 right there. And that is exactly what we're told to use. That Roman number 3 in between the words iron and oxygen, or iron and oxide, tells us the oxidation number of iron that's being used is +3. The total oxidation has to be -6, therefore iron must have a total oxidation of +6. +3 twice will give us that +6. There are 2 irons, and 2 times 3 is 6. Therefore, once again, that -2 3 times is going to give us -6. We need a +6. So what number twice is +6? That's +3. This will give us the 0 that we need, so iron 3 oxide is Fe2O3. Ready? The iron has an oxidation number of positive 3. Okay. Now, what about writing some other formulas? This one will be magnesium fluoride. We're going to use the oxidation numbers. All right, we're going to use the oxidation numbers. I had to clear off something that was from the old textbook. I want to make sure I get it right. Now, magnesium chloride. Okay, I'm going to start right here. Magnesium is Mg, and with an oxidation number of +2. I'm going to write that oxidation number right above the symbol. Chlorine is Cl with an oxidation number of -1. Now, does this total 0? Does +2 and -1 total 0? No. +2 and -1 totals +1. But I need the chlorine right here to be -2. So, what number, -1, how many times will give me a -2? -1 twice will give me a -2. That means my final answer is going to be MgCl, magnesium chloride, with the 2 right here, because I need that -1 written twice. And in a moment, you're going to see an even faster way to come up with this. And here we go. Magnesium has a +2. Chlorine has a -1. So once again, I'm going to write this out the longer way. Magnesium with a +2, chlorine with a -1. I need -1 twice to match that +2, and then my final answer is simply MgCl2. That's a pretty quick way to do. I wonder if there's an even faster way to do this. Well, I've come up with this shortcut right here. You see that 2 right there? It ended up here. You see that -1 right there? That ended up here. We just don't write the 1s in the formulas. What we simply did was switch the +2 and the -1, and we dropped their plus and minus signs. So here I had the +2 above the magnesium, I had the -1 above the chlorine, and look what happened. That 2 went here and dropped the plus sign, that 1 went here and dropped the minus sign, and we don't write the 1s in the formulas. So you got a little switcheroo trick which will work if and only if there are exactly 2 different elements. If there are more, we can't do that. We would use least common multiple in that case. So switcheroo, that'll get us the final answer. And then if we have to, we will reduce, and we'll have examples during our practice problems which will make us reduce. Ready? Okay. Here's some more examples. Iron 3 oxide. I know I showed you that a little while ago. Iron is +3, oxygen is -2. How are we going to write this? Well, this time we're told right there, use the +3, oxygen is the -2. Let's do this the long way first. I can't just say 2 2s make a 3. That won't work out. But again, I showed you this a while ago, least common multiple of 3 and 2 equals 6. So a +6 and a -6 will get me a 0. How many 3s make 6? 2 of them. How many 2s make 6? 3 of them. Now, what happened to the 3 and a 2? See how that 3 went down here and lost the plus sign, and that 2 went there and lost the minus sign? The switcheroo trick worked. Now, the switcheroo shortcut is nice, but the math verifies this will work. As I just showed you, the least common multiple of 3 and 2 is 6. So the formula Fe2O3 is the formula for rust. Oh, didn't turn on. Now it did. +3 -2. That 3 went there. That 2 went there. And the signs disappeared. Switcheroo works only because the math says so. But again, we have to have exactly 2 atoms involved in order for switcheroo to work. On the right side, phosphorus sulfide. Phosphorus +5 will give away 5 valence electrons. Sulfur, -2, will add on 2 electrons. What's the least common multiple of 5 and 2? Because I can't just say 2 times 2 is 5 or 2 times 3 is 5. That's not going to happen. What's the LCM of 5 and 2? 10. How many 5s make 10? 2 of them do. How many 2s make 10? 5 of them do. There's your formula. Look what happened. On the P plus 5, switch down to the S. The -2 on sulfur, switch down to the P. The 2 signs dropped. Your answer is P2S5. And we would read that as diphosphorus pentasulfide. All right, here it's just iron oxide, but iron 3 oxide, because that's the oxidation number of the iron before we did the little switcheroo trick. Ready? Polyatomic ions on your handout, the big boxes at the bottom, they're going to show those polyatomic ions. Okay, hydroxide is one of them here. So we're going to write the formula for magnesium hydroxide. And you look, and magnesium has an oxidation number, I'll use a different color so it doesn't blend in quite as easily, of +2. And you'll see on your handout, hydroxide is -1. Now remember, polyatomic ions are 2 or more atoms put together and pretend to act exactly like one. The parentheses tell us that the O and the H are together and pretending to be a single atom. Once again, our little switcheroo trick works. That 2 goes there, that 1 goes down here. Or, let's put that +2 and -1 back, we can realize how many 1s match that 2? 2 of them do. Does this total 0? Because that's now +2 and -2, which totals 0. The polyatomic ions work exactly the way as the single elements do. Here's baking soda, sodium bicarbonate. HCO3 is called bicarbonate. Sodium is a +1 and bicarbonate is a -1. That polyatomic ion will take on 1 more electron that sodium would love to give away. So just like with sodium chloride, a +1 and a -1, this already totals 0, so we don't have to do anything else. Remember, +1, -1, already done. Takes practice. You'll get used to it with the practice problems. Ready? Okay. Now, how do we name the compounds? We're given the formulas now, and we want to come up with the correct names. We're going to use all of the first name and alter the last name to IDE. Now, you noticed on a couple of these we had up there a little while ago, and you know from sodium and chlorine, NaCl becomes sodium chloride, especially in a binary compound. The last 3 letters of the second name will become IDE. Prefixes, if we have a covalent bond here, are going to tell us how many of the atoms there are, and these prefixes are going to go into our names, so we know by reading either the name or the formula exactly what the compound is. Ready? Here are the prefixes. Mono is 1. However, there's a rule for mono. Remember, water is H2O. This would be, I'll write this out, dihydrogen, mon, but we don't put monoxide. If the root word, the element name, starts with a vowel, we're going to drop this and just say monoxide. Okay? But there's a rule. Here's carbon dioxide, CO2. And all I'm going to write in the first name is carbon. We do not put mono on the first element, so I'm not going to write monocarbon, just carbon, and then to have room, I'll put it here, dioxide. Remember, that's carbon and oxygen, but as you saw on the last page, oxygen becomes oxide, and that's how we're going to write. Okay, di means 2, as you just saw, dihydrogen monoxide, and then carbon dioxide. You get something like tri, well, that's going to be a 3. Okay, ammonia, that smelly stuff that's in some household cleaners, that's NH3. That's nitrogen trihydride. Okay, if you have a 4, that's tetra. Okay, an example of that would be carbon tetrahydride, which is methane. And that's a gas that our bodies give off. That's carbon tetrahydride. Remember, we don't say monocarbon, just carbon. First element does not get mono. Penta, you saw P2S5 on the last page. You saw di, phosphorus pentasulfide, P2S5. And you get a hexa, okay? There's a gas, you know about helium, you breathe in some helium and you talk at a really high pitch. There's a gas called sodium hexafluoride, if I remember correctly, something like that. If you breathe that in, you get a really low, slow pitch in your voice. Okay. Sodium, actually it's not sodium, it's sulfur hexafluoride. And it gives you a really deep, slow pitch in your voice. Now, you don't want to breathe too many of that in, you don't want to breathe too much helium in either. But these are the prefixes we'll deal with. Mono 1, di 2, tri 3, tetra 4, penta 5, and hexa 6. Ready? All right, now chemical equations, I'm going to tell you up front, this is going to take a lot of practice. Some people get very quickly, and some need more and more practice. Hang in there, eventually you'll get it. Remember the law of conservation of matter. Okay, I'll give you a moment to think about that. Matter cannot be created or destroyed, but can change form. And in chemical reactions, what we have is a break apart of some bonds and a recombining of atoms into other bonds. What we have to do is make sure the equation's balanced, because we have to have exactly, and I mean exactly, the same number of atoms both before and after the reaction. Otherwise, the reaction is impossible to occur. So do a process called balancing equations, which I'm going to explain a lot better as we do the actual assignments. I'm just going to show you what a balanced equation looks like right here. Ready? Okay. In example equation number 1, we're combining iron and oxygen to get rust, which is iron 3 oxide. But look at this. There's only one atom of iron here to start with. Here's the reaction, and when we're done, we have 2 atoms of iron. Where'd that second one come from? Same with oxygen. We started with 2 and we ended up with 3. We can't do that. We have to start with and end with exactly the same number. Okay, very quickly, let's see how this works. But again, I'm going to explain it a lot better and more thoroughly as we do the practice problems. What's the least common multiple of 2 and 3? 6. So how many 2's make 6? 3 of them do. How many 3's make 6? 2 of them do. Notice I'm putting numbers in front of the formulas, nowhere else. I'm not splitting a formula apart, and I can't change the subscripts. Okay, this is now going to give me 6 oxygens and 6 oxygens right there. But by putting that 2 there, I just made Fe2 twice, so I made 4 irons. So I have to put a 4 here. If you get that, great. If not, it's okay, because we haven't tried any practices yet. Okay, now we have 4 irons on the left and 6 oxygens, and we also have 4 irons on the left and 6 oxygens. So this equation is now balanced. Unbalanced, without those coefficients, those numbers in front, we don't start and end with exactly the same thing. 1 atom of iron to the left, but 2 on the right. 2 atoms of oxygen on the left, but 3 on the right. Okay, if you need to, pause so you can write this down. However, once we balance, I showed you those numbers a moment ago, 4 atoms of iron, and 2 times 2 is 4 atoms of iron, 6 atoms of oxygen, and 6 atoms of oxygen. Remember distributive property. Okay, just like in math, we have something like 2 times 3x plus 4. Well, remember, it's 2 times 3x and 2 times 4, and we put them together. It's exactly the same here. This is iron twice. So it's 2 times 2 is 4 iron, and then that's O3 twice. That's 6 oxygen atoms. And that's because it's this molecule right here, and we have 2 of those. So what we really have is Fe2O3 and another Fe2O3. That's why we get 4 irons and 6 oxygens over here. It does take some practice and some getting used to. This is now balanced. We start with and end with the same number of each atom, just rearranged. Ready? Very close to the end here. Let's read this. Potassium phosphate, polyatomic ion, plus magnesium chloride. Okay, you can say pretty much anything for the arrow. In this case, I'll say recombine to form. So potassium phosphate and magnesium chloride recombine to form magnesium phosphate and potassium chloride. Now later we'll talk about the 4 kinds of chemical reactions. But look at all this. I can easily see right now 3 potassiums and only 1. This is not balanced. This will not happen. There is no what if. This will not happen. Now I can kind of see potassium atoms going away, but where did the second and third actually magnesiums come from when there was only 1 to start with? This is why we have to balance. Okay? This one's a little more complicated. I'm going to save the explanation of this for the practice problems, but here you see, let's go through. That 2 in front of this entire molecule, that's 6 potassiums. Now remember, don't go in the parentheses. As long as you have PO4 in the parentheses, you can kind of ignore this right here, and whatever's inside there you have twice. And you have 2 of those here. Here you have 3 magnesiums and 3 magnesiums. You have 3 times 2 is 6 chlorines and 6 chlorines and also 6 potassiums, which you have over here. That's going to take practice, but this is a balanced equation. We start with and end with the same things on both sides. The atoms are simply rearranged. That satisfies the law of conservation of matter. Ready? All right, so now you see a little bit of writing chemical formulas. Again, be patient if you didn't quite get it. These things take practice, especially balancing equations. But how did you react to this lesson? All right, we'll see you in class.